1. Our group member consists of me, Adrian Mong, and Ahmad Diaudi, Aina Alia, and Chiu Si-ying. I'll pass to my group member to start the presentation.
I'm Darren. For the report summary, experiment 2 is an experiment regarding flow measurement. Flow measurement experiment is an experiment to compare the discharge coefficients of different types of flow measurement methods. The different types of flow meters mentioned is orifice plate, nozzle, and venturimeter. These three flow meters is used under a series of procedures involving apparatus like manometers, rotometer, and valves like flow control, gate valves, and ventilation valves. The reading from the multi-tube manometer and rotometer is then taken for 5 different values of actual flow rate. The results are then used to calculate the theoretical flow rate to subsequently calculate the discharge coefficient for each manometer. Now I pass on to the next presenter.
Thank you, Deodin. So next, I am Ainalia and I will present about theory. So many types of device using principles of Bernoulli equation have been developed to measure fluid velocities and flow rates. So in this experiment, 3 common types of flow meters will be used, which include the orifice plate, nozzle, and venturi. The operation of each is based on the same physical principles, whereby an increase in velocity results in a decrease in pressure. So for an orifice plate, it is a restriction with an opening smaller than the pipe diameter, which is inserted in the pipe. Due to the smaller opening area, the fluid velocity will increase and hence causing a decrease in pressure. The flow rate can be calculated from the measured pressure drop across the orifice plate, which is P1 to P2. Thus, as the Bernoulli equation applied with the assumption of the flow is horizontal, steady, inviscid, and incompressible, the theoretical flow rate as well as the coefficient of discharge can be calculated. The nozzle applied the same principle and calculation as orifice plate, with only changes on the cross-sectional area of nozzle. The difference between them is only the shape of the restricted opening, whereby the nozzle is approximately a quarter ellipse. Last but not least, we have venturi. The venturi consists of a rapidly converging section, which increases the velocity of flow and hence reduces the pressure. It then returns to the original dimensions of the pipe by gently diverging the diffuser. Just like the nozzle, same principles and calculation as orifice plate applied to the venturi, with only changes on cross-sectional area of venturi. Okay, next we move on to procedures. So first, we need to ensure that the orifice plate is properly fixed at its position and fasten the manometer tubes, which is H1 and H2, to the orifice plate. Next, we need to close the flow control and the gate valves and then turn on the main switch and the pump. Next, we simultaneously slowly open the flow control and the gate valves until they reach their maximum opening level. And next, we need to open the ventilation valve by turning it to an anti-clockwise direction to release all the bubbles. Then we need to close the ventilation valve and then close the gate valve, turn off the pump. Next, we need to slowly open the ventilation valve until the minimum water level of 30 to 40 millimeter is reached, and then turn on the pump. Seventh, we need to slowly open the gate valve until the level of water in H1 reaches maximum 390 millimeter, and manometer H2 is at its minimum level. Record all the reading in multi-tube manometer and also the rotometer. Next, we need to record all the reading for 5 different values of Q actual by adjusting or reducing the opening of the gate valve. Next, we need to close the gate valve and turn off the pump. Remove the manometer tubes, which is H1 and H2, from the orifice plate. 10th, we need to change the orifice plate with the nozzle and repeat steps 1 to 10. Meanwhile, for the venturi, the manometer tubes are connected to H1 to H3, and similar steps of 1 to 10 are applied. Last but not least, after we finished, remove all the manometer tubes from the system, close the flow control valve, and turn off the pump and the main switch. Next, I will pass to the next presenter.
Thank you, Aina. Back to me again, Jordan, for the data analysis. For this experiment, we have 3 sets of table for each flow meters, for the 3 flow meters, which is nozzle, orifice plate, and venturimeter. For each table, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 columns, which is for Q rotometer, which is in liter per hour. Volume water collected, which is in liter. The time, which is in second. Actual flow rate, which is in meter cube per second. Theoretical flow rate, which is also in meter cube per second. The H1, H2, and the difference in H, which is in millimeter, and the coefficient of discharge, which is unitless. For the actual flow rate, we must convert from liter per hour in the Q rotometer into meter cube per second. For the theoretical flow rate, we must use the formula given in the manual. And lastly, for the discharge coefficient, we must use the formula Q actual over Q theoretical. Now I present to you the data and the results of our calculation. This is for nozzle, and this is for orifice plate, and last but not least, this is for the venturimeter. Now I pass on to the next presenter for the discussion.
Yeah. The first thing we discuss is the difference on water level in manometer with different types of flow meter, and we relate the answer with pressure losses associated with the types of flow meter. For the data result, we found out that the differences on water level for nozzles is 250 mm and decreases constantly at 35 mm when the value of Q rotometer decreasing of 100 for 5 times experiment testing. For orifice plate, the differences on water level is decreasing constantly from 295 mm and have a sudden drop at the fifth time from 145 mm to 10 mm. On the other hand, the differences on water level for the venturimeter decreases constantly for all the 5 trials of experiment. The higher the height differences, the bigger the pressure losses. From the experimental results, we can conclude that the venturimeter has the highest height differences, which is 355 mm, while the orifice plate 295 mm and the nozzle 250 mm. This can conclude that the venturimeter experienced the highest pressure losses, followed by orifice plate and last the nozzle. Next, we discuss about the differences in discharge coefficients value for each of the flow meter and the ranking of flow meter according to their accuracy. The differences in discharge coefficient value for the nozzle is between 0.84 to 0.88. The orifice plate is between 0.38 and 1.1, and the venturimeter 0.68 to 0.78. This shows that the nozzle experienced the smallest changes when comparing to the other two flow meter. Venturimeter placed at the second as it has slightly higher changes of 0.10, and the last, the orifice plate experienced the highest changes, which is 0.83. On the analysis above, we can conclude that the nozzle is the most accuracy tool when measuring the volumetric flow rate of fluid in a closed system, in a closed tube, followed by venturimeter and the last orifice plate, which is the most inaccuracy measuring tube. Next, I'll pass to the next presenter.
Hi, my name is Xin. Next, I will continue our discussion about the factors contributing to errors or inaccuracy in experimental data and the possible recommendations to improve the existing results. According to the experiment results, there are several errors that have an effect on the outcome. Because of the fluctuating flow rate in the pipe due to a lack of fully formed flow, it is difficult to read the water level accurately, particularly in the beginning of the experiment as the water flow is not steady. It is also difficult to set up a constant flow rate of water because of the fluctuating flow rate, especially when we need a constant volume of water collected at 3 liters. The start of timekeeping is not synchronized and may not be correctly initiated when the water level in the tank rises due to the experimental's different response time. Next, due to constraints such as the reader's height, which some might be too tall for, and other variables, parallax error occurs while reading the water tank level. Next, there are a number of methods for resolving or minimizing errors. The problem of obstructing water flow can be resolved by repeating the experiment and taking an average of the measurements. Next, we can take roughly 2 liters and measure it with a more sensitive instrument, such as a measuring cylinder, to solve the problem of taking a constant 2-liter volume of water. We can use a digital stopwatch instead of an analog stopwatch or other methods to increase timekeeping accuracy. Lastly, to avoid parallax error, we need to measure the water level is parallel to our eyes. Next, I will pass to next presenter. Thank you.
Okay, so for the conclusion, in this experiment, flow rate was measured by using a first meter, venturi meter, and the nozzle. The operation and characteristics of this measurement method can be determined by comparing the pressure drop measured in relation to the velocity of the fluid in the pipe using the Bernoulli and continuity equations. So according to the data collected, the energy losses for nozzle is significantly higher compared to orifice and venturi meters, while for the orifice plate, the energy losses are quite low but start to excess much energy as the flow rate is slowing down. Last but not least, the venturi shows that because of the lower head loss caused by its strapline structure, which almost prevents bonded layer separation and therefore type drag, the value obtained was similar to the real flow rate. As a consequence, the orifice plate has the lowest accuracy ratio, while the venturi and nozzle have the lowest error rate. So we can conclude that as the nozzle is ideal for high pressure application as well as energy recovery, we could conclude that the meter was more precise than the other 2 meters. Thank you.